Hello everybody, this is Rudrapradan here. Welcome to Engineering Econometrics. Today we will continue with model diagnostics. That too, in the last lecture we have discussed something about the multicollinearity problem, and then we have discussed some of the problems to address the multicollinearity issue and the kind of solution thereof. And in this lecture typically we will discuss similar kind of problem, and that too the concept of autocorrelation. First of all, what is exactly this autocorrelation problem, and we will address certain issues behind this autocorrelation problem. That too, what is exactly the autocorrelation issue, how to detect this problem, what are the reasons behind this particular involvement, and what will happen if that particular problem arise in the modeling, and then we will suggest certain guidelines or the kind of approach to the solution of autocorrelation problem. By the way, autocorrelation is a kind of problematic situation in the case of modeling any kind of econometrics modeling. When we discuss certain problems, and our usual approach is to fit the model, and then we must have the estimated model, and that will be used for any kind of prediction so far as a engineering problem is concerned. And before you start the prediction of a particular engineering problem, we like to justify that the estimated models which we have from the fitted data should be free from all kind of virus. That is the what we use the term called as a model diagnostics. And so here the issue is with respect to the error terms, and that too whether there is any kind of relationship exist among the errors which is usually derived through kind of estimation process. The thing is that we will go through the particular process, what is all about the autocorrelation, and how is this particular concept, and then we will think about the consequence, the kind of solutions and so on. Usually autocorrelation is a systematic pattern in the errors that can be either positive or negative. So, that means the nature of the relationship is not so important. What is important, whether there is a typical relationship exist among the error terms. So, that means when we regress any kind of error terms, so we will find okay. So, usually for a simple modeling, so let us say we have a y and x and then u. So, the structure of modeling, econometric modeling for any kind of engineering problem deals with the involvement of dependent variable, the involvement of independent variables, and the involvement of error term. Usually x and u are called as a independent variables, that too one is explained in nature, that is the x cluster, and u is the unexplained independent variable, that is the error cluster, and both has independent impact on the dependent variables. So, that means technically if we have a dependent variable here, let us say y, and then we have x variable here and then error term here. So, technically x must have an impact on u y, and u must have an impact on u, and then there is a kind of relationship between x and u. So, what is the model requirement? There should not be any relationship between x and u. Again within the x we have a multiple number of variables like x1, x2, x3 and so on. And then we under u we have also multiple number of variables, say u1, u2, u3 and so on. So, that means we like to equally check whether there is any relationship among the regressors, that too with respect to x and that too with respect to u. So, when we talk about the a relationship among the x, that to independent explained variable, and that particular approach is called as a multi-collinearity problem, which we have discussed in details in the last couple of lectures. And in this particular lectures we will be dealing with the error variables, which is nothing but u clusters. Now, having the u variables in the u vectors, so we can prepare a variance covariance matrix with respect to error terms. So, technically we can have error representation like this y1, u1, u2, u3 and so on, but in the meantime let us have a error covariance matrix with respect to u1, u2 and u3. So, ultimately we can have a variance covariance matrix, 3 into 3 variance covariance matrix, and then so this is called as sigma square u u1, this is called as a sigma square u2 and this is called as a sigma square u3, and then this is sigma u12 and this is sigma u13 and this is sigma u2 u1 and this is sigma u2 u3 and this is sigma u3 u1 and this is sigma u3 u2. So, that means we have for 3 independent error variables. So, we have variance covariance matrix of order 3. So, within this order 3 we have 3 diagonal elements, that is sigma square u1, sigma square u2, sigma square u3. So, that means sigma square u1, sigma square u2 and sigma square u3. So, this is one cluster and another cluster will be the error covariance, that too sigma u12, sigma u13, sigma u21, sigma u23 and sigma u31 and sigma u32. So, these are all 6 different covariance. Now, our discussion is with respect to autocorrelation problem. So, now in the with respect to the variance covariance matrix of error terms, we have 2 sets of problem, that too with respect to variance of the error terms and then with respect to covariance of the error terms. So, when we will be dealing with the covariance of the error terms, that is the problem is called as a autocorrelation. When we will be dealing with the variance of the error term, that is the problem called as heteroscedasticity problem. So, either heteroscedasticity or homoscedasticity. So, what is heteroscedasticity or what is homoscedasticity we will discuss in the next lecture, but in the meantime we will be dealing with now autocorrelation problem, and that too with respect to covariance of the error terms. So, in this case for having u1, u2, u3. So, we have couple of covariance like sigma u12, sigma u13, sigma u21, sigma u23 and then sigma u31 and sigma u32, and with these covariance, the requirement is that these covariance should be equal to 0, because our declaration is that the independent unexplained variable is independent one. So, since it is since the declaration is the independent variable, so there should not be any relationship between the two. So, if there is any such relationship, then that particular relationship is called as autocorrelation. So, technically, so the issue is like so with respect to error term, so we can have sigma square ui. That means technically it is better to write like covariance of ui and uj, which is equal to sigma square u for I equal to j, and covariance of covariance of uy uj which is equal to actually 0 for I not equal to j. Okay. So, when this will appear, then the problem is that the particular model is free from autocorrelation, but when this will happen, so that means covariance of ui equal to ui uj equal to sigma square u, where I equal to j. If that will happen, then this problem is called as a heteroscedasticity. So, now, so this is the situation of homoscedasticity, and this is the situation of no autocorrelation. Okay. So, now if this will not equal to sigma square u, so that means covariance of ui uj not equal to sigma square u when I equal to j, then this problem is called as heteroscedasticity problem. And when covariance of ui uj not equal to 0 for I not equal to j, then it is called as autocorrelation problem. So, that means technically our discussion is on autocorrelation problem. So, now, so the simple understanding of autocorrelation is like this. So, covariance of ui uj equal to not equal to 0 for I not equal to j. So, this is the simple mathematical notation of autocorrelation. So, that means in the simple language, so there should not be any relationship among the error terms. If there is any such a relationship or there is a correlation or covariance among these error terms, then this particular problem is called as autocorrelation problem. So, let us see how is this particular problem altogether, and we will discuss in details, right. So, this is what the problem, and with a simple understanding about the autocorrelation. So, we like to see whether the particular model is free from autocorrelation or is having autocorrelation. But in reality, most of the problems whenever you kind of the estimation and the kind of analysis, and when we are dealing with data to fit the model. So, autocorrelation is a kind of genuine problem, but what is the kind of tolerance level which you like to keep, so that the model can be used for decision making process or the kind of forecasting requirement of any kind of engineering problem. So, our job is to check what is the level of autocorrelation and whether that particular level is absolutely okay for any kind of decision making process. So, now in between we like to discuss what are the criteria through which you can detect this autocorrelation problem, and what are the regions through which it will be appear in the systems, and what is the typical consequence, and what is the kind of solution. So, these are the things we are supposed to target here. So, in the simple way if you ask what is exactly autocorrelation, so we have already discussed. So, it is the relationship among the regressors. So, the requirement is that there should not be any covariance or correlation among the error terms. If there is a such relationship, then the simple understanding is that there is a autocorrelation problem. So, now whatever we have discussed, this is what the kind of cross check. So, let us we have a model like this, and these models give the indication that y is equal to beta 0 sorry beta 1 plus beta 2 x 2 plus beta 3 x 3. So, that is called as 3 variable case. So, let us start with a simple model where y is a function of x 2 and x 3. Then the particular model will be equal is like this: y equal to beta 1 plus beta 2 x 2 beta 3 x 3 and the error term. So, this is the intercept, and this is the these are the slopes, and this is what the error terms. After the estimation process, we can have the magnitude of error term, and then we like to check the kind of relationship between these error terms. So, now so simple understanding what we have already discussed, covariance of u I u j equal to 0, that is the case of no autocorrelation, and when covariance of u I u j not equal to 0 for I not equal to j, that is the condition, then there is a kind of autocorrelation. So, in general, so the structure of autocorrelation can be written like this, because for a particular error component we can create a number of error terms by using simply a time lag. So, that is what the t minus edge is all about. So, for instance, you can create ut minus 1, ut minus 2 and so on. So, every time we have to check whether there is a relationship between ut minus 1, ut minus 2 and again ut minus 1, ut minus 2. So, there are n number of possible ways you can check the relationship and then come with the conclusion whether there is a kind of autocorrelations or there is no autocorrelation in the system. So, like this we will check and find out the kind of magnitude and the kind of solution there as per the particular requirement. So, now what will we do? So, this is what the simple mathematical understanding about the presence of autocorrelation in any kind of econometric modeling, that too when we process the the kind of solution for any kind of decision making. So, we have to estimate the model and check the model diagnostics, and here the diagnostic is with respect to error term, and the requirement is that the covariance among the error terms should be equal to 0, and if that is not the case, and that is the simple involvement of autocorrelation, or that to the presence of autocorrelation in the system. So, let us see how is this particular structuring. So, like what we have already discussed, it is similar like multicollinearity problem. In the case of multicollinearity, it is the game among the independent variable that is explained in nature, that is the X cluster, and here it is the similar kind of structure. We like to check the relationship among the regressor, that to unexplained independent variable, and that to among the error terms. So, like multicollinearity, the relation there is means there are two instances, either there is a relationship or there is no relationship. If there is a relationship, then there is autocorrelation. If there is no relationship, then there is no autocorrelation. Now, if there is autocorrelation, either it will be negative or it can be a positive. So, that means we are looking for covariance or correlation to quantify the relationship among the regressors. So, whether it is a positive one or negative one, we do not have such kind of issue. Ultimately, it is a problem whether they are negatively related or whether they are positively related. Ultimately, there is a relationship, and there is a autocorrelation, and we like to check whether the particular relationship is statistically significant or not, or it is within a limit or beyond the limit. So, we have a kind of tolerance kind of structure through which autocorrelation can means may not have any problem, but when it will cross a particular limit, it will have some kind of problem. It is exactly like multicollinearity case, where we use VIF. If VIF is actually single digit and that too close to 0, so the impact of multicollinearity is very less in the system, but here is also a similar case, and here like VIF. So, we have a component called as a DW statistics, that is called as Durbin Watson D statistics, which can give you the typical limit through which you can actually say whether there is a presence of autocorrelations or absence of autocorrelations, and if it is present under what condition or what magnitude, it will not create any problems. After that, it may create problem for any kind of management decision. So, obviously, the simple understanding is that so if the relationship is exactly 0, so no problem. If the relationship is not 0, so either it will be positive or negative. It may not be also means it may not also problem, but if the particular relationship is statistically significant, then it will be it will be a problem. So, we like to check whether it is actually statistically significant or it is going beyond the particular limit through which we cannot take a management decisions, or we cannot use this particular model for any kind of engineering decision. So, likewise, so we have already discussed. So, these are the kind of understanding through which you can project the autocorrelation. It may be with respect to cross sectional structure, it may be also with respect to time series structure, but more frequent means the particular problem is very frequent in the kind of time series clustering. So, when we have a time series data and using the log variable, then autocorrelation usually is a genuine problem, but when you are having cross sectional data, the counterpart heteroscedasticity will be the genuine problem. But by the way, when you have a models and that estimated model which is actually derived through the use of data. So, whether it is a cross sectional data or time series data. So, we have the estimated models, it is the mandatory requirement that we will check the model diagnostics, and that too the autocorrelation issue and heteroscedasticity issue. So, so let us see how is the kind of structure through which you can understand the particular problem. And if you ask what is the reason for the involvement of autocorrelation, there are many kind of regions. It is kind of multiple scenarios through which you can generate this problem. So, like if the mathematical functionality is wrong, and if the variable specification is wrong, and misspecification, that means technically misspecification of the variable, omitted variable case, and sometimes over identify models, and the use of the log variables, and sometimes when you manipulate the data and then increase the data size, means data structure through which actually look for the model accuracy. So, these are the instances, or these are the typical regions through which actually autocorrelation may be appearing in the systems. Then there are many different ways you can say it will address or it will involve in the problem. So, our job is to check and report what is the magnitude of autocorrelation, whether it is a 0 or non-zero, if it is a non-zero, to what extent. So, there are couple of ways you can check and report the particular item. So, likewise these are the various regions through which you can autocorrelation can be arise. So, now I will give you little bit specification what exactly the autocorrelation and how we can actually simply detect and and come with a kind of conclusion. So, basically it is a process outcome, and that too it is a step by step process. So, we start with the simple theory and develop a models, then connect with the data, then have the estimated model, then with the help of estimated models we can derive the error term, then the game will start to check the autocorrelation. So, like this so let us say this is actually a multiple equation model model. So, where we have one dependent variables and many independent variables, that two k independent variables, and then there is involvement of error terms. So, these are all called as explained independent variable, and these are all called as unexplained independent variables. So, now with the help of data and the use of OLS technique, we will get a estimated equation that is called as an U cap. So, by the way error term will be removed in the process. Now, the difference between actual y and the estimated y will give you the error terms. So, that is you can call as ut or et, but here we will use the term ut, and like to then we will check the kind of autocorrelation. So, mathematically if you say autocorrelation, then you just link with ut with previous log variables, that is ut minus 1, and this is called as a correlation coefficient rho. So, here the null hypothesis is that rho should equal to 0 against the alternative is rho not equal to 0. So, that means this rho coefficient, that is the correlation between ut and ut minus 1, and that value should not be statistically significant. If that is significant, then there is a presence of autocorrelation, and that is that too it is dangerous for any kind of decision making process. So, now I will give you little bit better understanding if you like to know how this actually term related to each other. For instance, in this case simply ut equal to ut minus 1. So, that means technically it is a question of ut and ut minus 1, that to this case ut equal to ut minus 1, that to function of ut minus 1. So, now again the ut minus 1s may be function of ut minus 2, again ut minus 2 can be a function of ut minus 3. So, it is like chain. So, so obviously there will be definitely presence of relationship among these error terms. So, our duty is to check and find out the magnitude, whether it is actually under the tolerance or beyond the tolerance. So, likewise we will see how is the particular structure, and ultimately like correlation coefficient, the autocorrelation coefficient range is also between minus 1 to 1s like here. So, what we have already discussed, it may be the negative one or it may be the positive one, but ultimately there is a relationship, and that relationship should not be so high and should not be statistically significant while using this estimated model for any kind of decision making process. And ultimately rho is the symbol here to get to know the kind of presence or absence of autocorrelation. So, now the simple modeling kind of structures, that means you start with the simply y equal to beta 0 plus beta 1 x 1 t plus u t, and then u t is a function of rho u t minus 1 plus v t, another error terms, and rho is the kind of autocorrelation coefficient. Then either rho will be equal to 0 or not equal to 0. If it is 0, then no autocorrelation, and if it is not equal to 0, it may be approaching towards minus 1, and if that is the case, it is called as a negative autocorrelation, and if not, then it will be approaching towards plus 1, then this will be called as positive autocorrelation. If we exactly plus 1, then it is called as a perfect positive autocorrelation. If it is exactly minus 1, it is called as a perfect negative autocorrelation. And likewise, so the nature may be positive, the nature may be negative, but we have no issue whether it is a positive or negative, but ultimately we will check what is the label. So, this is how the kind of graphical plotting about the error terms, and we like to check whether there is a kind of functional form among the error terms. If there is a functional form by default, so there is a kind of autocorrelation, and that too it will give you some kind of indication about the model kind of diagnostics, and ultimately so we can graphically inspect, but so far as a quantification is concerned, we can actually find out the autocorrelation coefficient, that is the rho here, and then we check whether it is actually problematic case or not problematic case. Of course, there are a couple of methods, technical methods are there to get to know the level of autocorrelations, and then we can check the kind of tolerance limit. So, one such statistic which I have already highlighted is the Durbin-Watson D statistics, and Durbin-Watson statistics, the structure is that when rho equal to 0, dw statistic will be exactly equal to 2. So, that means actually Durbin-Watson D statistic structure is like this. So, that means actually when I am connecting with actually ut upon ut minus 1. So, then I can find out the autocorrelation coefficient. Then with a particular setups, we can calculate Durbin-Watson D statistic, that is small d here. So, it is simply the equation equal to 2 into 1 minus rho. So, when rho equal to 0 technically, then we have already declared there is a no autocorrelation, and when rho not equal to 0, there is a autocorrelation. So, now when we put rho equal to 0 where the signal is no autocorrelation, then by default in this case d exactly equal to 2. So, now when rho not equal to 0, then the d value Durbin version d value, it may deviate actually above than 2 or less than 2. So, as a result, so dw statistic will be here 2 is the kind of extreme. So, when exactly equal to 2, dw statistic exactly equal to 2, then there is no autocorrelation. Otherwise, it may have autocorrelation whether it is less of it or whether it is more of it. But technically, if you talk about the tolerance, then we can have range here 1.5 and we can range here actually 2.5. So, now in between, if the Durbin Watson statistic will lie, then this will not be serious problem so far as decision making process is concerned. Otherwise, it will be a serious problem. So, these are all different orders through which actually UT is related, and that means it will give you some kind of high order autocorrelation when all these error terms are correlated each other over the time, and then at the end of the day you will find the involvement of autocorrelation is at the highest level, and that too it will be a danger signal for any kind of decision making process. So, likewise we will check and get to know what is the level of autocorrelation. And by the way, after knowing the detection of autocorrelation, we are very keen to know the kind of consequence and the kind of solution. So, but as a consequence is concerned, so the model simply cannot be used for prediction, forecasting or any kind of decision making, and because most of the instances the variables will be not significant, because this will increase the standard error of the estimates, and as a result the variables involved in the particular modeling will not be significant. So, not all the variables kind of requirement, but some of the variables may be not significant, and that may be because of the presence of autocorrelation. And simple understanding is that when autocorrelation is there, standard error of the estimates will be very high, and it simply actually affect the significance levels of the parameter. When it will affect the significance level of the parameter, then as a result that particular variable will not significant for the model estimation or the kind of model forecasting. So, now we will have a different kind of detection criteria, which I have already highlighted a graphical mechanism, and I have also given you the technical mechanism. But the best way to represent the autocorrelation is through Durbin Watson D statistic, because it will give you a kind of quantitative structure through which you can actually exactly identify the autocorrelation issue, whether the kind of autocorrelation level is there or not there. So, that means when Durbin Watson D statistic exactly equal to 2, then there is no autocorrelations. If not, then there is a autocorrelation. Again, if it is within between 1.5 to 2.5, that can be acceptable. Otherwise, you just restructure the model and have different output. Again, check the model diagnostics and that autocorrelation, and see whether the restructuring model is again free from autocorrelation. Once you get a model which is actually under the control, then you can use for decision making process. So, until unless you get the clean or green environment, you should not actually use this model for any kind of decision making process. So, these are different graphical plotting through which you can check whether there is a kind of relationship, and this is another way of checking the kind of presence of autocorrelation. And Durbin, and this is what the Durbin Watson D statistics, and it is a typically step by steps process. First to connect dependent variable to independent variable, have the estimated model, get the error terms, and then connect error term with the previous error terms and get the autocorrelation coefficient. After knowing the autocorrelation coefficient, you can get to know whether there is a presence of autocorrelation or absence of autocorrelation problem. That means technically if dw is exactly equal to 2, no autocorrelation. If not, then there is a autocorrelation. This is the simple understanding or the kind of check which you can do in the process of modeling. That is how among all the tests, Durbin-Watson statistic is very good ones, and most of the softwares will provide the DW statistic directly without going through the step by step process. So, what you can do, just you run the model, have the DW statistic and check what is the accuracy of the models. If the accuracy of model is okay, then the DW statistic by default will support the kind of accuracy of the model by having actually DW statistic D close to 2. If not, then it add the problems, so that we cannot actually use for any kind of decision making process. So, that is the procedure through which actually you can go ahead with the decisions. And while using Durbin-Watson statistic for decision making process, that to declare the presence of autocorrelation or absence of autocorrelation. So, the simple approach is dw must be exactly equal to 2, no autocorrelation. If not, it may be positive, it may be negative, but there is extremes. Like autocorrelation coefficient can simply range between -1 to +1. So, that means technically if you will see here, so dw statistic will be simply written like 2 equal 2 into 1 minus rho. Rho is the autocorrelation coefficient, and autocorrelation coefficient, and then when rho equal to 0, then d equal to 2, that means there is a no autocorrelation situation. When rho equal to, that means rho will vary from -1 to 1. So, in between the 0 will be coming into the picture. So, that means 0 is the middle one, and when you will put rho equal to -1, then it becomes actually a dw statistic will be 4, and when we will put actually rho equal to exactly 1, then dw statistic will be 0. So, so when the autocorrelation coefficient is moving from -1 to 1, that is the usual limit. So, the Durbin-Watson d statistic will vary from 0 to 4. So, that means technically d will be ranging from 0 to 4 with high positive autocorrelation to high negative autocorrelation. Ultimately, ideal range is dw should be exactly equal to 2, and if not ideal, then it may be negative or positive, but it is dangerous when the dw will be exactly equal to 0 or dw exactly equal to 4. So, that means any dw statistic will be close towards 0 or close towards 4 is a more danger signal, and in that case you cannot just use the model for any kind of decision making process. So, you have to restructure, re-estimate, redefine, then you look for the alternatives and again check, then finally you should accept the model which is exactly free from autocorrelation or else within the particular tolerance range, that too between 1.5 to 2.5. So, this is how the kind of check process of Durbin-Watson d statistic through which you can take a decision. And with this we will stop here. In the next class I will take this problem and then calculate manually the dw statistic, and we can report what is the level of Durbin-Watson d statistic and whether there is a need of further restructuring to solve the autocorrelation problem, provided if the autocorrelation is coming very high. Thank you very much. Have a nice day.